last lecture, we talked about eigenpositions, and we used the equation L by state rho equals lambda by state rho to determine our eigenposition over here, given a linear transformation and its corresponding eigenvalue. And basically, eigenpositions are basically people in our given system that don't change, or they stay under a span. So yeah, I'm not gonna do the picture. You guys can just check the previous lecture on that. And we also talked about dynamic. So dynamic, which is some function alpha that maps our given system O cross D. Not really O cross D. I mean our position state space. Our position state space, which I think I denote by boldface B, blackboard boldface B, onto a new space. I think it was F. I forgot the notation. I did lecture this year on Saturday, so I kind of forgot it. So it alpha maps P onto some other space that was something real, I suppose. Yeah, real. So R. Yeah. So R percent. R percent. Or R with R equipped with the percentage symbol. So R equipped with the percentage symbol. Just call it like that. And this this operation percent just simply fixes R onto itself. So what it does, R is R, of course, an A inside R, I mean only R, an A inside R, our value in R is fixed by this percentage operation onto A percent for all A in R. Okay, so that was the last lecture. This is the last lecture. Percentage mapping sort of our position state space onto another space. I believe it was just R or some other space in the previous lecture. It's just a one-dimensional space. It's more of like an interval. It's more of an interval. So we can actually think of this as from minus infinity percent up to positive infinity percent. Positive infinity percent, where an A inside this interval, minus infinity percent, positive infinity percent, is an interval, is an element of the real numbers, or the integers if you want to restrict it to discrete values rather than decimals. So if you want to just say 5%, 10%, 20%, you can say that instead A is an element of the integers. But the integers itself is a subset of the real numbers. So it can still be part of the integers. You can still define an A that's an integer, or a percentage as an integer, and it would still ring with our intuition here. Okay, and yeah. Basically, yeah, eigenpositions, and we solved for an eigenposition given a linear transform yesterday. So today, I suppose we're gonna begin talking about vector calculus. Okay, so let's start first with vector fields. So what about vector fields? Well, vector fields are not really vector spaces. I just want to state right off the bat that vector field is not the same as a vector space. Now Now what makes the what separates this with this is that a vector field is not really a set, but it can be thought of as a function. This is more of a function, not really a linear transformation, but a function. Well, this is a set. This is a set of vectors. Well, this is a function that takes in some vector space or some coordinate system or space, and then gives us some field that that has vectors on all points. So as I stated in the video on my building intuition video, a vector field is the notion of assigning every point on a space with a corresponding vector. So if I'm going to use our O cross D space, so what our vector field, I'll call it blackboard O-face F, is it maps our system O cross P, not D, onto some O cross P, onto another O cross P, but this O cross P now, instead of points, contains vectors now. But it's not necessarily a vector space. And so we characterize this vector field, this F, as some two multivariable functions. So I'll say Q1 of x, y by I hat plus Q2 x, y by j hat. So this is our vector field function, or function that generates a vector field. Or we can just write it via vector notation. Q1 of x, y and Q2 of x, y. You can write like that. Since we're using I hat and j hat notation anyway, so you can write it like this or like this. And so what this would look like, is something like this. So we have our system. I'm gonna use it. We have our system. You guys can see this. Okay, we have our system, and then we have vectors. Let's say that the center has positive divergence. So our vectors will go like this. And then you guys can probably fill out the rest of your imagination. So basically assigning every point to a vector, and to know the vector at a point, we just need to evaluate a point, or we just need to evaluate the function at the given point. So to find out this vector over here, we just need to know its point, or where its what its point is. So where its tail sits at is the point here. So I'll call the x value A, and I'll call the y value B. So to find this vector over here that I'm pointing at, we just need to plug A and B into the equation. So let's say that this vector field is generated by F equals Q1, Q2 of x, y. Then to find this vector, we just need to plug A. So F at this point P equals AB is equal to just Q of 1 evaluated at AB, and then Q2 at AB. And as you can see, even though we have two vectors here, we would still come up with even though we have two functions over here, two variable functions, we would still get a vector output, because ultimately we have that I hat and that j hat term, which turns the input into a vector of some form. So the tail sits here, and then the vector that we get from evaluating this function is where the head sits at. Okay. So if I'm just gonna write it here, this head over here sits at QAB and then Q2AB, or rather it's this component over here and this component. So this times I hat and this times j hat. So this is For I hat is this one, and then for j hat is this one, this component over here. Okay. So this is Q1. Say Q1 AB. Q1 AB. And this is Q2 AB. I don't know if you guys can see it. But we just evaluate there, and then we get the sort of the head, where the head sits at. So that's the concept of a vector field. So I just gave you guys a picture of what it is. It's not a set, again, it's not a set, but it's what it is, it's the notion of assigning a given field or a given set of points with a corresponding vector. Okay, so with that, now, okay, so there are many ways of interpreting a vector field. So with our original notions of vector spaces, we can think of a vector field as something that models a certain behavior. So it can be something that governs, I suppose, behavior of a certain person. Though, even though we can model behavior of a person here theoretically, it's all theory. It's not applicable. You can't apply this in real life. It's not really what it is. Human behavior is much more complex than this. So think of it as just a mathematical exercise, as with this entire course. So, right. So, you guys remember my differential equations video, right? Where I discuss about differential equations, what they are, what they model real life phenomena. Now there are these things called phase spaces, or slope fields, that really tells us, or it helps us in finding solutions for a differential equation. And they look like vector fields, but instead of vectors, we have lines that dictate what the slope is at certain points now. So instead of vectors, every point is assigned with a slope that a solution to the differential equation follows, right? So for example, if I'm gonna run out a picture here, there, see, we have slopes like this. Let's say this is the slope field of a given problem, right? A given differential equation. Now, what we just want to say is that, okay, obviously these guys move in an arc, a lopsided arc, and then they move inwards onto zero, or they have negative slope approaching zero, and then positive slope coming away from zero, right? So, what function would solve this, or what function would follow the flow? And that function would be something like a parabola, a parabolic function, something like ax squared plus some constant b. So it's like this. That follows it. So this is a solution to the differential equation that generates the slope field. And so to generate a slope field, it's roughly the same thing as generating a vector field. We just plug points in our given differential equation. And since our differential equation defines the slope at every point, we just get a slope for each of these guys, right? Because since we have a differential equation, right, you get the slopes of the function at various points once we generate the slope field. And we just need to find a function that follows the flow at every point of these guys. It follows the slope of these guys at these points. Okay, so that's a good correlation, but what does this have to do with our study? Well, vector fields can be a good way to model things. So in real life, they're actually applied in engineering and in various other fields, most notably quantum mechanics, but mostly engineering, to model fluid flow. So when I first found out about vector fields, the first thing that came to mind is fluid flow. So the flow of water around an arbitrary surface. Let's say a circle. Let's say water is flowing around the circle. Obviously, what if we have water flowing this way? We want water to flow this way. Well, of course, they would keep going. Pretend these lines are vectors. Okay, it's hard to just individually draw vectors, so I'll just write them as lines or as dots. So of course they're gonna go like this, and then some of them are gonna go like that, and then some are probably gonna make vortices or bump into here, and then just move on with the flow. There's some will probably diverge, Generally, yeah, this is best described as a vector field over here. And then some sticks for a while, and then sort of divergence. So if we hit water, or if we have a water spray or water hose hitting the surface from here while it's submerged under liquid, this would roughly be what it would look like, right? So, yeah, I suppose it's a good way of modeling, or not only fluid flow, but vector fields are also used to model stuff up above, like planetary orbits or motion, gravity. So, like, let's say this is Earth, and then this is our moon. Not the scale, by the way. Let's say this is Earth, this is our moon, and this is a satellite. A satellite around Earth. Now, this has the least amount of vectors pointing towards it because it has so little mass compared to Earth, which has a lot of vectors pointing towards it. It's not sun. It's just these are vectors pointing towards Earth. Vectors pointing towards Earth. And well, when we draw vector fields, if we actually follow what our function tells us about the vectors that we get, it would be very long. They would go all over the place. They would overlap. So what we do to simplify things and make it look more cleaner is that we lie a bit. We cheat a little bit or lie a bit, and instead of using length to denote the magnitude of the vectors, we use color. Now I don't have color here. I only have blue and black, but just pretend that these guys have a big gravitational attraction, okay? So these guys have the largest one, and then the moon only has, only about 1% of that. So it's very small vectors. Very small compared to the Earth's. And now you guys can see that vector fields are a great way of modeling this, because if we have something that's flowing by, or if we have a spacecraft or a heavenly body like an asteroid moving through space, they would be pulled in, and of course they'll impact either here or they'll impact here. So they get attracted, and it's a good way of showing us where they would go, or at least model, or at least attempt to model where they would go, is via vector fields. And so you guys can now see how we can apply this into our study. And that application comes into, modeling things, of course, like human behavior, or the behavior of gender fluid people. Now this is something that is going to be discussed in your queerology course. Your basic queerology course involves fluctuations, of course, and gender fluid people, as well as femboyology. As early as femboyology, or in your advanced queerology courses, you guys will notice that most people in today's society tend to fluctuate back and forth, and a good way of modeling that is via vector fields. And any function that follows this vector field or this phase space is a great model for it. So it's also a great way to sort of model what states would do. So if we have a given person, right? I'll draw a system. I'll draw another system. Let's make another picture. So suppose we have a vector field, and then let's say our vectors want anything here to tend towards 0. Okay. So what if we have something here? It's going to go on to 0. So it tends to go to 0. So just write that like this. So the more you're up here, the heavier you're gonna fall down, and then the more you're here, the slower you fall down. It's sort of like a Gabriel's horn type thing. We'll call this the origin. So, and then like this also. Okay, let's add a little bit more vectors here. Okay. Okay, so suppose we have a person that's over here. We have a person over here, right? There's, let's say that this is O cross D. Okay, O, and then this is D. Okay, O cross D. So we have an orientation over here. No, appearance. No, O cross P. Sorry, this is P. Rather, not really P, but let's call this time. So instead of P, this time we have a O cross T. So we're now looking we're describing our orientation, or rather appearance, or dynamic. I believe this is the dynamic, dynamic, with respect to time. So suppose that it's governed by this kind of function. We don't know it at the moment. It doesn't matter. So suppose it's governed like this, and we have a person that's over here. So they're currently in the dominant position, and as time goes on, they sort of tend to neutralize and balance themselves out. So they're neither dominant nor submissive. As so what the vector field tells us is, as this point, as we allow time to move forward, the point follows the flow of the vector field. Okay, the flow this person follows the flow of the vector field, and then it sort of just rides the waves. You can think of it that way. So like how water follows the flow in a sort of moving current, person here follows the flow of the vector field and tends towards zero. Of course, this is arbitrary, and we don't know the actual function that generates this just yet. You guys can tell me in the comments what it is, but that doesn't matter. What I want you guys to understand is that when we talk about vector fields, we think of something that follows the flow of it. So if we have a point here, a vector determines where it is at that point, which is of course determined by our plugging of the point at the function, and then at the second time frame it moves and follows the vector. So the next instance of the thing or the person, I'm gonna erase a part here so I can give you guys a picture. So suppose we have a guy that's following this vector over here. Okay, he's heading down. So this arrowhead over here, the point where this arrow lands is the next point in time where it continues, and then so it goes like this. And then, of course, same thing. The end point at where this arrowhead lands at is the next point in time, and so it just follows the flow, keeps going on and on until it sort of balances this out, or it just keeps going off into infinity. This is a ray after all, it's an interval. So that's the basic concept of how we apply a vector field to our function, to our study. And this is actually going to be a bit shorter than other lectures, I believe, because there's nothing really much in the way of vector fields. Of course, we already discussed our generating function that generates our vector field is composed of two or three of those guys. If we have a three-dimensional vector field, I believe it's given with three component functions, right? So a q1, q2, and q3 of x, y, z. So what I showed you guys a while ago, this f is a two. What I'm saying is a two-dimensional vector field. One-dimensional vector field is possible, though it's not that interesting. It just tells us like how fast the point moves on a given interval, or yeah. Now this one here gives us a plane now. It's not really just an interval. It gives us two intervals now, and then we have points. And of course that's our vector field is determined by this of course our q1 of xy and our q2 of xy. A three-dimensional function now, three-dimensional vector function, which gives us of course three axes to work with. So an x, a y, and a z. And then now here, I'll call F3 is this. So now it's composed of three components now. So it now has a q1, x, y, z. So a q2 of x, y, z. And then we have a q3 of x, y, z. And now this time we're multiplying by the respective components I hat, j hat, and k hat. Where k hat is of course the unit vector going upwards in the z direction. Okay. And so now this time we have vectors pointing upwards. Now instead of just having a length and a magnitude, they now have a height. They now have a height. We now have somewhere we can point upwards with respect to the horizontal. Yeah. There, we now have a z-plane. Now, of course, a four-dimensional vector field is harder to imagine, though we can think of it as sort of like a Minkowski space, wherein I suppose we have another component vector here, at q4, but this time we have something like a t hat. That would start to move on to I would say we start delving into complex number territory, and it'd be best to explain in terms of quaternions or complex numbers. But we want to stick with the stuff that keeps us sane for now. Okay. So yeah, there are two very important properties of a vector space. A vector field. Sorry. And these two important properties is the curl and the divergence, which I talked about in the building intuition episode. Now you guys know that a curl of a given vector field, say a two-dimensional vector field, is of course, the cross product between our F2 and our Laplacian operator. You guys remember our Laplacian operator of order 1, of course. And then our divergence of F2 is just the dot product. Divergence. And these are evaluated at points. So if you want to know how much vectors curl around a point, or if you want to know the curl of a vector field, specifically at a point, then you evaluate this expression at that point, right? To be more precise. And I defined it in our previous video already. It's given our component vectors. So this would just be the determinant of this matrix. So I hat, j hat, and then our I believe it's like this. It looks like this. And it's just 0, I suppose, because 0 is just all zeros here. Because we can only take determinants of a square matrix, I suppose. Yeah, I believe it's just 0 because we don't have a k component, but we do have two components here. So I had the g hat in this direction. Yes, it keeps us in the two-dimensional plane. So this, and then d, dx, and then dy, and then q1, and then q2. I believe. If you guys have any corrections, just tell me. But it's below. Yeah, I believe it's. Well, I said in the previous video, or in the building tuitions episode. And so now, as I said, given a vector field, of course, our curl tells us how much points rotate around the point. Okay. So and now divergence also tells us how much the rate of how vectors move away from a point, right? So if it has positive divergence, it means that vectors move out of the outside, and if it's negative, we have a convergence, so points move inwards. And so now the thing that's good about these things, or knowing about these definitions, is that when we define our vector space, vector fields, that people, of course, that we use to model behaviors of people, like say gender fluid people, that fluctuates back and forth between two genders, male, female, assumably, or presumably male, female. We say that it has no divergence. So it has no holes in it, it has no divergence, and it has no curl in it. So that means the curl is, it's mostly near 0, of course. I mean, after all, there are points wherein it goes around. So of course, there's some positive curl there, and then there are some points where it goes under. So there's negative curl. There's points where, yeah, because it's a sine wave after all. Just go back and forth. It's like a sine wave, so it goes back and forth. So there are points wherein it's positive and negative curl. So I wouldn't say that there's no curl. So yeah, but there's no divergence after. There's really no divergence because there are no vectors. If we model some fluctuating phenomena, if we model some fluctuating phenomena, there's no breaks. Okay, these aren't discontinuous points. I just wanna let's say make it as close as possible so that you guys will know that they still intersect with the. Like say something like this. Now as you can see here, there are no vectors that move outwards because I didn't write them. Not only because I didn't write them, because really there is no divergence defined over here. Well, of course over here you can see that it sort of goes away here, but that doesn't really matter. It doesn't concern us. Although, if we make this a family of sine curves, we could show that there is a sine curve that goes like this. It's just, well, this sine curve, I suppose, minus pi. Yeah, this point is like pi. If we minus it, we shift it to the left by pi units. So that would give us something like this. Something like I believe this is like a cosine. So I suppose, no, this is definitely a cosine root, and then this sine. Yeah, this is sine. Yeah, this is sine. And we have some another sine wave such that of course pi 0 is just 0. Yeah, pi 0 is 0. Or at 0. The function, well, evaluated at 0 is 0 instead of just evaluate at pi 0, of course. So 0 is a root in this case. And this and then of course we have some divergence here, over here. After all, it goes there, it goes here, goes here, goes here. Vectors go here upwards. But it's of no concern to us. And of course, you can see that there is only some divergence over here, goes here, but some goes inwards over here, right? It goes inwards here. Vectors point inwards here according to our function. Of course, we can break this up into vectors. So instead of segments, we have vectors here that dictate flow. So these are vectors, like I said. No arrows, no arrowheads, because it's cumbersome to keep writing them. So I'm just gonna say it's line segments. Though these are not slopes. These are vectors. So yeah, of course now we have vectors that's pointing inwards towards here, since our flow is going this way. There are some that points towards this point over here. But the thing is, we define now our divergence as some piecewise function, such that, well, here it's not continuous because we have negative divergence here, and then positive divergence here, negative divergence here, positive divergence here. So what do we choose? Does it have divergence or does it not have divergence? So we just assume that it doesn't have divergence. Because it's really going to confuse us if we attempt to define divergence at that point. If we try to evaluate our curl at that point, yeah, it's going to give us some definite value, but it's best to just not define it because it would confuse us, because we have some here that is a negative and then this is a positive curl. And then here, our curl is not defined in this part and this part because we didn't draw arrows, or really it's not really defined that way. So yeah. Good way of modeling behavior. So, and the original topic for this is actually dynamic, for modeling dynamic. So, vector fields as models for dynamic. There. But yeah, that's pretty much it. You can just think of the t, and then this time we have our y-axis as our dynamic, basically. Oh, remember d. So maps p onto d. Or alpha. Okay, and so now basically we can just rephrase what I said in the building intuition episode, and then say that, well, curl just basically tells us how vectors around it tend. So persons around that person would react, or how they would sort of go around that point. So have a person over here, just a stationary vector, I suppose, and then we have some vectors going around this point. So position vectors. I'll call it row 1, and then row 2, and then row 3. Not really 3, but row 3. So guys tend around, and then the curl tells us what their lengths are. And maybe even implies how many there are around this point, which I will call P0, P0. So our point P0, or our point P0 is not the person, but how these guys react to it is the curl of the vector field that generates these vectors, of course. So if you try to construct a vector field for that basically tells us or governs the behavior of a certain individual that you know, just know that you also have to take into consideration what other vectors would do around that vector or at that point. So what you want to do when you construct a vector field that sort of describes behavior is that you say first that it has zero divergence at all points. So it doesn't diverge from any point. But of course, we have some vectors that go away from said points, but there will be those vectors that sort of go inwards into the point. But I'm not saying that you should define all vector fields as zeros, but rather just be cautious when we define divergence in a given vector field. So I suppose we'll carry the lecture forward by making our ninth definition. Definition 9. And position vector field. Position field. Definition 9. A position field, which I will call P, blackboard bold P, not really blackboard bold. Let's call it just P. Pn of dimension n. Dimension is a vector field is a function that assigns points let's say x y of a product of x cross y. Or we'll use R O cross D, O cross P. O cross P. O cross P. That says points O cross P with corresponding vectors. With a corresponding, which is given by the equation, which is our generating function. So then is q1 is dot qn of x1. Or actually, we'll generalize this. We're generalizing it. It's x2 x2 xn. Okay. So our Pn is of dimension n. So we have n variables in our subfunctions, or the functions that make up Pn. Okay. So I'll redefine it here, which is E1, which is our first basis vector. 1 hat Q1 plus dot plus En hat Qn. Lastly, where E hat N is the nth basis vector of O cross P. So it's really in the end this is really generalized. So this is a generalized thing. Okay. This is well not really O, but our axis, our first axis, A cross the dot A. X1, X2, Xn in well capital X cross the dot cross X. So now our two-dimensional case is just basically X1 and X2 and then just X cross itself. Okay. So there. So now I suppose so. As a homework or as an exercise, I encourage you guys to discover a couple or construct a couple vector spaces, a couple position fields that you guys think will model some real life people. So like I suppose gender fluid people. Try to find a vector field that sort of models them, something like that. I'll just find a way to erase that later. So yeah, I know this lecture wasn't really that long. So that's it for this vector field. So in the next one, we're gonna probably conclude the course by talking about the connection of our study to Yaoi and the Omegaverse. Of course, we're gonna be applying some concepts from biology, including the concept of a Yaoi set. A very important one, that one. A Yaoi set, after all. And then we're gonna talk about systems of position, so position vectors, and then we just gotta find what they are. So an example of that would be something like rho 1 plus rho 2 equals rho 3 P rho 3. Wherein, of course, two or more of these guys are given already, and then we want to find one or two of them, right? Or so maybe some arbitrary constant a multiplied by rho 2 equals rho 3 plus rho 1. Something like that. We want to find the solutions to these kind of equations. That's what we want to do in the next video. And of course, we're going to be also including switching positions also. So we're going to discuss some techniques. So first we're going to talk about the intuition behind them. So what it means to solve a system of equations. Also, well, of course, we're going to do some examples of solving them. And then we're going to discuss about Kramer's rule, which is a very useful shortcut when solving these guys. It's really a formula, not really a rule, but a formula for solving systems of equations. So see you then in the next lecture.